This problem gives us a conducting loop immersed in an external magnetic field, and it asks us to find the direction of the induced current in three different situations. We'll do this using Faraday's law and Lenz's law. Faraday's law tells us the induced EMF equals minus the time derivative of the magnetic flux. In this case, it's the magnetic flux through the area enclosed by the loop. Lenz's law tells us the induced effect always opposes any change in that flux. In part A, the magnitude of the external field increases. As that field increases, the magnetic flux through the area enclosed by the circle increases, and from Lenz's law, the induced effect will counter that increase. So the induced magnetic field must be opposite the external magnetic field. I'll draw that here in orange. Then we know from the right-hand rule that the induced current must be in this direction. So as the magnetic field lines circulate around the current, inside the area of the loop, the induced magnetic field will be directed out of the screen in the way that I've shown it here. So that induced current is in the counterclockwise direction. In part B, we have the opposite effect. The external magnetic field is getting weaker over time. That tends to decrease the magnetic flux through the loop's area, and Lenz's law tells us the induced field will counter that decrease. So the induced magnetic field must be in the same direction as the external field. From the right-hand rule, we see the current must be in this direction so that as the magnetic field lines circulate around it, inside the area of the loop, those magnetic field lines are directed into the screen as I've shown them here. The induced current in this case is in the clockwise direction. In part C, there's no change to the magnitude of the external field, so there's no change in the magnetic flux through the loop's area, and there's no induced EMF or current.